Number 17 here. This index, just as we're working through there, if that's an even number, you always have to take the radicand and make sure that it is greater than or equal to 0. Okay? Always have to do that, no matter what the radicand is. Okay? Now, if it's an odd number, for instance, let's say it's, I'm going to zoom in here a little bit.
I had one where it was 5.
Yeah, everybody had one where it was eventually 5. But if that's an odd number, think about this. Can you take the, let's just go with 3 right now. Can you take the third root of 8? Can you think of something that multiplies by itself 3 times to give you 8? 2. Can you take the cube root of 0? Can you think about something you multiply by itself 3 times to get 0? 0. Can you take the cube root of negative 8? Negative 2. Okay, because cube root is a number that multiplies by itself 3 times to get the radicand, right? So because of the multiplicity of negatives, we can actually take the odd root of negative numbers. So you took the odd root of positive, you took the odd root of 0, you took the odd root of negatives. We can take the odd root of anything. So when they ask me the odd root of x squared minus 9x, it's all real numbers. The domain is all real numbers. The only time that we have issues with roots is when you're taking an even root. Now, a square root is what we've been dealing with for the most part, but a fourth root is the square root of a square root. So, in order to take that first square root, I obviously have to have a defined value to do that for, okay? And then to take the second, to ultimately eventually get to the ability to take the second square root. So you don't, if that's a 4 or a 6 or an 8 or a 12 or a 200, you don't treat this process any different. You just look at the fact that it's even. Okay? Is there a question?
Yeah. Can it be a 0 if the radical?
Yeah.
Okay.
Yeah.
I thought that was what
If the radical is in the numerator, you can include 0. If it's in the denominator, you got to exclude it. So we got two kind of approaches that you can do here. Okay? A lot of us are probably maybe going to factor this, I would think, as x minus 3, x plus 3. Set that greater than or equal to 0. Maybe some of us said, oh, I know that maybe using the square root method is this, so that's eventually going to give me plus or minus 3 for x, right? Maybe I should write it this way. X equals plus or minus 3. Regardless of how you go about doing that, those are going to be your zeros, right? Okay. Now here's what's going on graphically. You guys know from Algebra 1 and Algebra 2 that x squared looks like that, right? That is your x squared, we call it the parent function for that function. X squared minus 9 drags that thing down 9 units. You guys remember talking about transformations last year?
Wait, Mr. Bay?
Yeah.
I thought it was x squared minus 9x.
Oh, is it 9x? Okay. My fault. What we did last class was just minus 9. All right, so not a hard fix. All right, so we got x squared minus 9x is greater than or equal to 0, right? So that's the GCF of x. So we factor that out as this. Okay? Now, we're going to solve this like it's an equation initially to see where do we actually cross the x-axis. Okay? So what x squared minus 9x does, so we, again, from previous math courses, we know that our parabola, x squared, looks like that. Okay? What the x squared minus 9x does to that is it's going to take it, it's going to move it, and drop it kind of like that. Okay? And we'll learn in the next couple chapters how we know that it does that, how it kind of moves the vertex into ultimately the fourth quadrant here. And then I get this x-intercept here of 0, and this x-intercept here of 9. Does that make sense? And that's what these values are symbolizing. Okay? We want to know, when is x squared minus 9x greater than 0 or above the x-axis? Because these are y values, right? Okay, that's a rule for me to generate y values. I want to know, when are my y values above the x-axis? Well, does it make sense graphically that this location, those are my y values that are above the x-axis? Are these y values that are above the x-axis? Yeah. And those are y values that are positive, right? That's what we're asking here with this question. When can I have a radicand of x squared minus 9x to be positive? So what we do then is we identify the x values in which this occurs for. So over here in this blue, it's everything from negative infinity up to 0. Now you can include 0 because we have that equality. And then we union, so everything that's red here is below, right? All these are negative. So I don't want to incorporate those. And then everything to the right of 9 would be positive. Okay? Now you can check those values and make sure that when I plug them into x squared minus 9x, I do get a positive number. I like to check the ones that are negative. If I check like 1, I get 1 minus 9, that's negative 8. Is negative 8 greater than or equal to 0? No, and that's why I know that I didn't put that in my interval. Okay? So that's the graphical approach. Okay, and that's the underlying process for what I'll show you next, which is the procedural thing, that maybe when we do it procedurally, we lose context. We lose an understanding of what the math is actually telling us. Yes?
Are we going to have time for the quiz to graph like that whenever you want?
So tomorrow's quiz, I'm not going to give you a radicand that you have to factor and do this kind of stuff with. We've only done sign charts for a day and a half. In a couple weeks, we'll hit sign charts again with rational functions, and that's when I'll quiz you over sign charts. With this, though, if I'm thinking about a sign chart, okay, so not saying we don't even know how to do this, because when we get to these irrational functions, we will, I'll say, hey, remember about 2-3 weeks ago we did this? And then we'll pick up from there, okay? So I won't introduce this fully at that point. But what we do is we create a number line, and this number line models the x-axis, okay? So it models that thing right there. So we need our zeros on it, 0 and 9. And then yesterday we talked about how we put the factors on the side. We put x, that was one of our factors. We put x minus 9, that was our other factor. And we put our total. If we remember our total was x squared minus 9x, or, in a factored form, x times x minus 9. So my total is ultimately telling me, or giving me instruction on how I find my total, is through the multiplication of these two things, right? Does that make sense? Okay. So, as we're working through this, and I like to put little dotted lines here to kind of segment my number line into regions. I now have 3 regions, right? But those 3 regions, guys, are analogous, or corresponding to, or comparable to the 3 regions in my XY axes that I create with those vertical green lines. Does that make sense? Okay. Do you see we have stuff over here to the left of 0, which would be this stuff here? Does that make sense? We have stuff in the middle of 0 and 9, which would be that stuff there. And then we have stuff to the right of 9, which would be that there. Does that make sense? Okay. That was kind of dumb of me to do because now I got to erase all that garbage. This thing doesn't always want to cooperate. All right, so what we do then in the sign chart, okay, is we start choosing values that are to the left of these zeros. Okay, so I'm going to choose a number to the left of that 0, 0. So I'm going to choose just something random and very large. Because then when I plug in the X, don't I just get back that number? So it would be a negative Y value. Okay, so out at negative 100, this is going to contribute to my product a negative amount. At negative 1,000, this is going to be negative. So this factor is going to contribute to my product a negative amount. If I have two factors that are both negative, their product then becomes positive, right? Okay? So what this total line here, or row, is going to get to, or kind of be compared to, is that to the left of 0, your Y values are positive. Is that what our graph is showing right here? To the left of 0, your Y values are positive. So this row is showing me what my Y values are doing in comparison to the 0 and 9 on the x-axis, and those regions that are defined by it. So then when I go to 0 and 9, I should get a negative here eventually, right? If we look at the graph here, so when I choose, let's just say, 6 is in there, right? If I choose 6, then I get 6, which would be a positive number there. Positive number. If I choose 6, it'd be 6 minus 9, which would be a negative. What's a positive times a negative? A negative, and that's why we're seeing here over in our graph, those values are below the x-axis. They're negative Y values. Then over here, if I choose a very large number, plug in for x, you get that number back, so you get 1,000, which is positive. 1,000 minus 9, positive. I can choose real big numbers because when I subtract something small, it doesn't really impact it very much, right? So it allows me to do that substitution pretty quickly, pretty easily. And then that would be a positive times a positive because it's a positive. Does that model then what we're seeing right there? Okay? So when we do a sign chart, guys, I want you to understand that a sign chart is a cryptic way of showing you or graphing your function in the XY axis. It doesn't give me necessarily the specific ordered pairs, but it does tell me whether my Y values are positive or my X values, my Y values are positive or my Y values are negative in certain regions. Does that make sense? Okay. It's up to you, especially right now when it's x squared minus, so it's going to provide a parabola. Okay. If you understand parabolas pretty well, maybe you don't need a sign chart. Okay. Eventually, we'll talk about cubics. If you understand cubics, maybe you don't need a sign chart. Okay. But eventually, like chapter 4 will be something like this. It'll be like x to the 4th minus 3x cubed minus 7x squared plus 7x over, or plus 9 over maybe 3x squared minus 6x plus 9. And this function is going to probably look something, I don't know, probably look something maybe like this when we graph it. That could be completely wrong, but it's going to be messy looking. And we want to figure out, well, where is this thing positive, where is it negative, that kind of stuff. A sign chart is going to be much easier, much more concise than actually graphing this thing. Does that make sense? So that's kind of where we're going with that. Any other questions in that assignment? We didn't do anything but go over homework questions in the last class, so kind of want to do the same thing with you guys. Anything?
I'll get a lot for you. Well, I'll get on the computer and look.
Absolutely. I've never yelled at you.
That is very cool. Number
20?
20? Well, I was messing with you said you're going to keep that class.
I did. It was disrespectful.
Well, really, said that you face
That hurts my feelings, Cole. Okay. So this is This is very likely to show up on tomorrow's quiz. Okay, it's something of this nature. When we have fractions and we have square roots, we have to think about them in the fact that denominators being 0 provide problems, and radicals that are negative, even roots that are negative, provide problems as well, right? Okay? So here's my question. What if I did this? That changes the complete understanding of this question. It changes the complete domain. Okay? So let's go back to the square root, answer that, and then see what it looks like when we do the cube root underneath. It's a very different solution. Okay? Or potentially a different solution. Maybe it's not. We'll see. The idea, though, is that thing right there, is there ever a number that I plug into x and get undefined back for x to the fourth? No. No matter what you plug into x in the numerator, you're going to get a number back. So basically what we need to do then is figure out, okay, what values in the denominator will I get numbers back for that I can actually divide my numerator by? Okay? We know that 0 is an issue, right? Even though 0 is a number, I can't take a numerator and divide it by 0. So that's the number, that's one restriction. But there's also a radical down there, and there could be a potential. Let's say if I had like 6 as x. When I get I in the bottom, do you know what 5 divided by I is? You don't, right? Okay? So that's not a real number. So we have to be able to figure out both those situations. When is that bottom going to be 0, and when is that bottom going to start giving me values of I back? Okay? So because the radical, we take the radicand, and we set it greater than 0. Okay? Now, traditionally, every radical we talk about is either going to be set greater than or equal to 0 or greater than 0. Now, why did I choose greater than 0 here? Because it's in the denominator. So if the radical is in the numerator, greater than or equal to. If it's in the denominator, just greater than. Because we're not allowed to be 0, right, in denominators? So that's why we make that differentiation. Okay? So now I'm going to, I think I would probably add x to both sides, and that's going to allow me to get to the answer a lot quicker. But there was another question from the last class that somebody asked, and something like this happened, and they said, well, I subtracted 5 from both sides. Got negative x is greater than negative 5, and they said, well, I divided by negative 1, and I got that. And they were wrong, right, because they did not switch the sign. So we got to make sure that we do switch the sign. Okay, so dividing or multiplying by negative, change the direction of the inequality, and it should be, what, positive 5? Okay. So now we're saying x has got to be less than 5. So less than 5 would be negative infinity up to 5 with a parenthesis. If you put equality in there, you get the same exact interval, but the parenthesis is in a bracket, right? So you have an infinite number of solutions that match, but you have one solution of 5 that doesn't really work. Okay, so, and on tests and quizzes, guys, if I ask what the domain is, and you mess up a parenthesis and make it a bracket, or a bracket and make it a parenthesis, that's going to make it wrong. All right, and you're going to argue, oh, it's just one little technical thing. Yes, it is, but in regards to mathematics, remember, one bad number, one wrong answer contradicts an infinite number of correct answers. Okay, so we got to make sure that we understand that. Does that help with that one, Cole? Let's talk about that real quick. If we have, so it's x to the fourth over the cube root 5 minus x, right? Okay. Can I take the cube root of a negative? Yeah. Can I take the cube root of 0? Yeah. Can I take the cube root of a positive? Yeah. So you might think, well, I can do anything. This domain is all real numbers. Okay. So maybe I start with a domain that is all real numbers, but now I got to think. Well, what if I did put 5 in here? What if I did take the cube root of 0? I'd have x to the fourth, whatever that is, so it'd be 5 to the fourth. What's that, 625? Okay, and then I would have 0 on the bottom. I can't do that, right? So what number needs kicked out? 5, so negative infinity to 5 union 5 to positive infinity, you recognize that that is a completely different domain just by changing the index of the root. $21. Why do you do that to yourself? Well, why do you, before the assignment is due, you run through all your attempts before you have the opportunity to ask questions? It is absolutely true. That's exactly what you just did. All right, find the domain of the function. Numerator. Numerator, x plus 9 squared. What's that? Is that a square root or cube root or fourth root or anything like that? Polynomial, right? Okay, that's x squared plus 18x plus 81. That's polynomial. So the numerator is all real numbers. You can plug anything in that numerator you want to. So no matter what you plug in, you'll get a real number back in my numerator. So then I got to look on the bottom. If I'm going to divide, I know I can't divide by 0, and I can't divide by things like I, right? Negative square roots. So I'm going to take 6x minus 1, and I'm going to make it what? Greater than 0. So 6x is greater than 1/6. Oh, greater than 1. And now x is greater than 1/6. X is greater than 1/6. Will be that interval there. Mm-hmm. What's the question?
You plug it in.
Okay, so the range, so you're talking about question 3? All right, so question 3, and I don't like this because it makes you start to make inferences about procedures that are not always true. So if you notice this assignment, you get through it, first couple start asking about domain and range, right? And then the remaining questions only ask you about domain. And the reason for that is because there's not right now a really nice way to find the range. But they ask it on these because there's specific types of problems, or they give you specific types of domains that allow substitution to work. Okay, so if I'm thinking about the domain of this, normally if I'm just looking at 3x, the domain is all real numbers, right? But here they give you a restriction. They tell you you're only allowed to use a domain of -6 to 7. Okay, so they're taking our graph and saying, okay, if it's 3x, that line there is 3x. Okay, let's say that we're only interested in it from -6 to +7. So we cut off all this part of the graph and we cut off all that part, right? Well, if I have -6 as this x value right here, how do I find that y value that goes with it? I plug it in. So that y value would be -18, right? If this is 7, that x value right there is 7, how do I find the y value that goes with it? Plug it in, right? And I get 21. So looking at my range, then range is always going from bottom up. The first y value you would encounter on this would be -18. The last one would be 21. Okay? And so you start seeing a couple examples like that. You say, oh, it's just substitution. I substitute the first domain value, and I get my first range value. Substitute my second domain value, I get my second range value. What if I looked at a parabola? Let's just look at x squared. Between -2 and 3. Okay? If I did that, so my domain here is -2 to 3. If I substitute into x squared, doesn't it give me a range of 4 and a range of 9? Is 4 and 9 the only y values on that graph? No. So substitution is not a good technique for finding the range by just using the input and the endpoints of your domain. So on questions that ask you for the range in WebAssign, they're ultimately saying we've set the domain up so that you can plug them in. But it's not something that is a procedure that you want to use all the time. Does that make sense? Later on, when we talk about inverses, we might have a better way of finding ranges. But right now, the best way to find a range is to graph it.
on the quiz tomorrow?
On the quiz, I'm not going to ask. If I ask you a range tomorrow on the quiz, you will have the graph in front of you. Everything else will be domains from the equations.
So is this quiz like